Hi, I'm Tally, and this is my final project. I'll be walking us through how PageRank, which is the algorithm behind Google's search engine, uses random walks on graphs to produce rankings. We'll explore the math behind it and connect it to the concepts we've studied in class. So let's get started. First, we're going to start off with an introduction on what PageRank is and how we rank web pages. PageRank was developed by Google founders and ranks websites by importance. The key idea is a page is important if other important pages link to it. That leads us to a mathematical model based on directed graphs and probability. Graph model. The first step in modeling the web mathematically as a directed graph or digraph. The vertices represent the web pages, and the directed edges or arcs represent the hyperlinks between pages. This connects to our study of graph theory in class. The out degree of a vertex, which is the number of links leaving a page, is crucial as it determines the probability of moving to a specific page. For example, on the diagram on the slide, page A links to B and C. If a person is on page A and clicks a link at random, they have a probability of 50% of moving to B and 50% of moving to C. That brings us to the concept of a random walk. PageRank models a random walk. We imagine an individual clicking links at random, moving through the graph. This process is mathematically described by a Markov chain where the probability of the next page depends only on the current page. This ties to the concepts of reoccurrence relations and connectivity we've studied. We capture these movement probabilities in a transition matrix P. Okay, for a simple example, let's imagine pages A, B, and C. A links to B and C, B links only to C, and C links only to A. The transition matrix P, shown here, is a column stochastic, meaning every column sums to 1. This represents the certainty that an individual will move somewhere from the current page while clicking links, which leads us to the stationary distribution. The key to the ranking is the stationary distribution of that random walk. The stationary distribution is a vector x where the entries x represent the long-term probability of the individual being on that page. This is the PageRank vector. The core mathematics lies in finding the solution to the system x equals px. Finding this vector x is an eigenvector problem. Pages with a higher long-term probability, a higher entry in the vector x, are considered more important and are ranked higher. In the example we just discussed, page C ends up with the highest score because it receives links from both A and B, as seen on the bar graph on the slide, which overall accumulates more importance. Next is the Google matrix. In the real world, the web graph is messy. It has pages with no outgoing links and disconnected sections, which break the strong connectivity needed for a unique stationary distribution. To fix this, PageRank introduces a modification called the Google matrix M, as shown on the screen. This blends the translation matrix P with a teleportation step. With probability alpha, an individual follows a link as in the original matrix P, but with the probability 1 minus alpha, they then can teleport to a random page. The result is the Google matrix M. This adjustment guarantees the necessary properties, which mathematically ensures a unique stationary distribution. And finally, we're going to talk about how you commute the PageRank vector x, which is through the power method. The steps of the power method are shown on the screen. And overall, this process is a reoccurrence relation, exactly like the type we've studied in class. The Google matrix M guarantees that this process stabilizes and converges to the unique PageRank vector. And then to tie it all together, our biggest takeaways are PageRank is a perfect demonstration of how discrete mathematics powers real-world algorithms. The structure of the web is a directed graph, and the search process is a random walk leading to a stationary distribution as seen through recurrence relations and probability. And then the final result of that is the PageRank vector, which provides the rankings. By applying concepts like graphs and digraphs, connectivity test, vertex degrees, reoccurrence relation, and algorithm analysis, we see how the math from our class provides the foundation for this algorithm. And yep, that's all I have. Thanks.